Hello everyone and welcome to ML Done. In this video, we're going to create a convolutional neural network for the task of multi-label classification. Particularly, I'm going to be using a pre-trained ResNet-18 model for doing this. And when I say pre-trained, it's because it's already been trained on a different data set, and we're going to use those trained features, those trained weights, to sort of facilitate the training process for a multi-label classification. Stay with me. Right, so let's get started. The first thing that we have to do is to import from torch.nn, we're going to import nn. This is the package that would allow us to define different types of layers when we are defining a PyTorch convolutional neural network. And by layer, I mean a convolutional layer or a batch norm layer or a fully connected layer and so on and so forth, as well as certain operational layers like tanh or ReLU nonlinearity functions. So that's a crucial package to import. Number two is from torchvision.models. I'm going to be importing ResNet18 weights. Now, this is the thing that would allow me to so that when I'm actually loading ResNet18, I'm going to be using this sub package to tell ResNet that, look, I know that you're a huge neural network with all these weights, but I want to use the pre-trained weights that are already there in you. I want to use the pre-trained version of you. I don't want to train you from scratch. Okay, so it will not initialize its weights randomly right off the bat. I just want to first help you get comfortable with this ResNet18 model, like what is inside of it. First, from the models that we have, like this is under torchvision.models. I'm going to be importing ResNet18, right? And as the arguments here, now this is the part that makes it load its pre-trained weights. And when I run this, it's going to load the pre-trained ResNet model. Now, I keep saying pre-trained. The reason is ResNet18 has already been trained. I mean, these weights are the result of a training on a huge data set called the ImageNet data set that I have it loaded up here. It's a image data set. It has all sorts of images in it. It's a task of multi-class classification. It's not multi-label, as far as I know. It's just multi-class classification. And you've got 1,000 images, image classes, basically. So given an image, the network has learned to assign that image to one of the 1,000 image categories. Now, obviously, in our example, we don't have 1,000 image categories, right? We have, I think, around 10 classes or something like that. Now, here, when I'm running this code, it will load. Oops, actually, it's nice that these errors happen. Well, the reason that error happened is because models has not been imported. So I believe if I say from torchvision import models, this should resolve the issue. Okay, now let's see what is inside this ResNet model. So you immediately see that there's a lot of things going on here. So it has a convolutional layer, and it's basically a conv2D layer, 3 input channels, 64 output channels, the kernel size, stride, padding, and so on and so forth. We have a batch norm layer, we have a ReLU layer. Like, by the way, these ReLU and batch norm, these are the things that you can actually build using the NN sub package that you have already loaded. If you want to define a particular layer, that's when you use NN. Maxpool, and here you have a sequential layer that has a bunch of different types of layers inside of it. Conv1, like we have a convolutional batch norm, ReLU convolutional batch norm. We have a block here, we have another block. So it just keeps going and going and going. At the very end of it, this is the bit that I want to draw your attention to. At the very last layer, we have a fully connected layer. It's a linear kind of layer. It has 512 inputs and it has 1,000 outputs. And why 1000 is because it has been trained on the ImageNet dataset. And as I said, we have 1000 different image classes here. So given an input image, this monster needs to assign that into either of the 1000 outputs. And that's why the number of outputs is 1000 here. And if I want to filter this fully connected layer out, I just say model.fc, and you see, like, it basically filters out only the layer that I'm interested in. Like, just to warm up, you can even say, okay, from model.fc, I'm just interested in knowing what's the number of input features, and or even the number of output features here, just as simple as that. That's the beauty of object-oriented programming. You can just call stuff when you put a dot there. If you have any object, you can access to any of the attributes inside. So basically, this fully connected layer is, if you want to look at the weights and the parameters inside of it, it's basically a 512 by 1000 matrix of weights, basically. And it also has a bias. So that's a bias unit that will have 1000 elements inside of it. We need to make sure that we will replace this layer with a different linear layer that has 1000, instead of 1000 output, it would have as many number of outputs as the number of classes that we have in our data set. And I want to draw your attention to the crucial point that all the parameters that exist in this huge model, all the weights have been pre-trained for ImageNet dataset. Now, the second we replace this final layer for our particular multi-label classification problem, immediately the weights that will replace this layer are going to be starting from like randomly from scratch. They will have no connection whatsoever to the ImageNet dataset. And when we train our neural network, we have the choice to either train the entire network or just focus on the sort of parameters of the fully connected layer that we have added. Of course, we're going to do the former, but I just wanted to point out that be aware of this sort of nuanced point here. Now, let's build our model. In PyTorch, when you want to create a neural network, you would define a kind of class. And that class needs to inherit from the nn.module class, which would give you all the nice abilities of parameter sort of tracking and sort of keeping track of the gradients and so on and so forth. It basically helps you build a computational graph in which you can track everything. And that's the recommended PyTorch method of creating an artificial neural network in PyTorch. Now, I'm going to be calling this class as MLC, which is multi-label classification. So class MLC, and I'm going to inherit from PyTorch module. Right. Now, when we define a class in Python, we always know that we have to have a constructor for this class, which means that the second you create an object of a class, the constructor is called automatically upon creating the object. Now, remember that PyTorch already comes in the nn.module class already. In that parent class, it comes with a constructor with all sorts of very nice attributes and functionalities that would allow you to do, your forward pass, backward pass, particularly keeping track of the parameters, the learnable parameters of your model. And that is why the recommended method and the method that you see everywhere when creating a PyTorch neural network is that you always basically keep the entire constructor of the parent class of the nn.module. So you keep that in your constructor, whatever it has, and then you have the ability to actually add whatever you want specific to your own application. But you don't want to throw any of the capabilities that nn.module classes constructor give you. You don't want to get rid of any of that. Now, what I said can be summarized in this. You define the constructor, and in here, in my constructor, you always have the keyword self, which sort of points to the object of the class, which is the instance that you will build from this class. And you have the ability to pass whatever number of parameters you want in here, right? So I'm just going to pass, I think, the number of classes. This is a design choice, by the way. It all depends on how you want to do it. Now, before I do anything, by anything I mean create my ResNet model, replace the fully connected layer with a new fully connected layer at the end. Before I do any of that, I just want to say, look, I want you to keep whatever functionality is there in the constructor of nn.module parent class. Keep all of that, then I'm going to add on top of that. All right? And that whole thing will become the constructor of my class MLC class. Sorry, in my class MLC, yeah, right? In order to do that, you would use the super method in Python. And you would pass MLC, which is the number, the name of the class, and the keyword self. And here's the magic part that you say that, look, from the parent of MLC, which is nn.module, I want to keep anything that is inside its constructor. And the constructor is always called with the dunder function init. So I'm just going to say dot, and I'm interested in the init function. Enter. That's it. You're keeping everything. Now, I'm going to create the ResNet model, ResNet-18. I'm going to make sure that it's the pre-trained ResNet model. Then I'm going to basically replace the final fully connected layer with a new fully connected layer that has as many number of neurons in the outputs as I have as number of classes in my application. This part is actually what I already had. Self.model is equal to models.ResNet18, ResNet18, right? And I'm going to pass exactly like what I did before. I'm going to pass the weights as the pre-trained weights, right? So I've loaded the pre-trained ResNet model. Because I want to replace the fully connected layer, and remember that the fully connected layer has, in this example, has 512 in features and 1000 out features. So imagine that I haven't seen how many in features it has. Like logically, if you have any convolutional neural network that you want to replace the final layer, you will have to retrieve the number of in features that linear layer has, rather than having to look into it directly. And that is why I showed you how you can actually retrieve the exact value of it here. Right, so I'm gonna say that self.in features is equal to whatever number of in features that fully connected layer has, which we know that is 512, but whatever it is, I don't care. I'm retrieving it in a smart way, right? Whatever, if it's ResNet-18, 256, I don't care. With this line, I can get it, right? But we know that it's 512. So now that I know it, and I also know that how many classes I will have in my neural network as the output, or this is going to be the out features of the fully connected layer that I'm going to be adding. Now I can actually create this fully connected layer, and I'm going to put it at the end of my, or let's say replace the fully connected layer of my current ResNet-18 model with the newly built fully connected layer that I'm going to create right now. So how will you create a linear layer? It's pretty easy. This is where the NN package that I talked to you about will come into play. So I can say NN.linear, and this is where you have to define the number of in features, the number of out features, as well as whether we have, yeah, that's it. By default, it will come with a bias unit as well. So self.in features is what we have as the input, as the number of input features, and the number of output features is going to be number of classes. So this is why I put this as an argument for the constructor, because I want to be able to dynamically, upon creating an object, dictate the number of output neurons that this object or this neural network will have to have, right? So how are we going to actually replace our current fully connected layer with this newly created layer? It's very simple. We're just going to say in my model, which is self.model. Actually, let's call this ResNet. Yeah. I'm going to put ResNet here. Self.ResNet dot fully connected. So the entire fully connected layer, I want it to become this newly created fully connected layer. And that's it. That's it. So this constructor now will create a convolutional neural network for me with whatever number of classes that I dictated to have. And the second part of creating a PyTorch neural network class is to define the forward method. Now this is again very easy. It's called the forward method here. Again, you have yourself here, and of course the input, which is whatever the input data is to your neural network. I'm just going to call it X. In our case, it's going to be just images. And what will happen is this X needs to travel through the entire neural network, right, that you've created. And the entire neural network is self.ResNet, right? So in other words, I'm just going to say X equals self.ResNet given X. You see, as simple as that. You just pass X to your neural network and it spits out the final output, and that becomes the result of your forward pass. And then you simply return X. Now let's create an object of this class. Let's say that the number of classes here is 10. So you, like any other, object-oriented sort of language, you just put the number of the name of the class here, and you pass the argument or the parameter, and then I'm going to call it my model. So if you run this, it will create an object of the class, and if you want to look at the actual layers inside, remember that you will have to access the ResNet, the self.ResNet that you have here, to actually look at what is inside. And before I press enter, just pause the video and try to answer this question. What will change in the output compared to the kind of output that you saw here when we looked at ResNet-18 in the very beginning? Pause the video and try to answer that question. And if you were not able to, that's totally fine. So if you look at the model inside, I think you can convince yourself that everything is the same except that final layer. And you notice that the input features is 512, but the output features is 10. The weights in here, the 512 and 10 matrix of weights plus the 10 values in the bias weight vector, they've been created from scratch and randomly, right? But every other weight here has been imported from whatever it is in the pre-trained ResNet-18 model, right? The parameters in an artificial neural network will basically have this sort of important flag that you might have heard of, and it's called requires _ grad, which can be true or false. If it's true, it means that you can actually calculate the gradients of your error function with respect to that parameter and actually learn that parameter, update it, which is machine learning, basically. And if it's false, it means that you will not be able to calculate the gradients with respect to it, and you will not be able to learn it. Okay? Now, I just want to make sure that all the parameters in my created neural network here has the requires grad flag as true. So in order to do that, I can actually print out all of these parameters. Now here's a very sort of nice way of actually iterating through the parameters of your model. So in model.resnet named parameters. This is the very nice sort of function that you can use, which will return the name of the parameter as well as the actual parameter itself. And inside parameter, you can look at the value of the parameter, or you can look at the particular flag or let's say attribute inside the parameter. I'm going to be printing the name of the parameter alongside whether the requires grad flag is true or false. And I'm hoping to see everything to be true, okay? Otherwise, if anything is false, that means I will not be able to train it. So when you print, it's nice to know that all the parameters have the requires grad as true. And you see what I mean by the name. You can see like conv1 layer dot weight is the first parameter matrix here. Conv1, or let's say batch norm layer dot weight is the second block of parameters, which again is true in terms of requires grad, and so on and so forth. You see this sort of nice hierarchical way of naming these parameters. That will help with the design and also recalling or calling these particular parameters if we ever wanted to, the same way that we easily called the fully connected layer. Okay, and I just want to also show you what is inside these parameters, because we've been talking about them a lot. Let me just show you all of the parameters first. It's going to be really messy, but I mean, I just want you to see everything. So again, it's the same sort of loop, but I'm just going to say if param.requires grad is true, which means if you are a kind of parameter that I can train, then I'm going to be printing your name and the data inside of you. So this is typically how you do it, but the thing is, we already know that everything requires grad as true, so I don't need that condition anymore. So if I actually print this, you see, as I said, it's huge. I mean, you see this is the weight tensor inside conv1, right? You see all these values. I mean, if I keep going down, I just want to show you, like, this is a conv2 weight tensor, and you see all of them are of the type tensor. These are particularly a torch tensor type, and all of them have one thing in common, and it's that they all have requires grad as true. But I want to also show you the fully connected layer. Can I call that data? Or wait. Yeah. So these are the weights inside my fully connected layer. And the last bit, we talked about the bias unit, but we never actually showed you how you can actually look at what is inside. And if you look at the bias, perfect. So you will have 10 values here, and again, requires grad as true. It means that you can train these weights as well. Okay, that's it. Now you know how you can create a convolutional neural network for the task of multi-label classification. And I hope that this has been informative for you. If you liked the video, please make sure that you will leave a like. And if you have any questions, make sure that you will leave them in the comment section down below. I always appreciate it. Thank you very much for being with me. Take care.